So now we're going to talk about what are known as the simple gas laws. Boyle's law describes the relationship between the pressure of a gas and its volume, because the pressure does depend in part on the volume of the gas. So if we keep the temperature of the gas and the amount of gas the same, don't let those change, then the pressure of the gas will increase when we decrease the volume. The pressure will decrease when we increase the volume. So here's a bicycle pump. A bicycle pump has a one-way valve here that only lets air in, and so the only place that the air can go out is through the tube into your bike tire. So when you pull up on the bicycle pump, you are increasing the volume inside that tube, right? When you do that, that decreases the pressure inside the bicycle pump. So now the pressure outside is greater, and so the air will rush in to fill that up. Now, when you press down, pressure, when you put pressure on it and squeeze it down, the smaller volume, now the pressure is larger. And the pressure causes the gas to go through here and into your bike tire. Because if you just open the valve on your bike tire, air is not going to just rush in magically, is it? Any air that was in there above atmospheric pressure will come out. Gas laws, remember, a law just describes what is. So the gas laws describe the relationships between properties of gases. Robert Boyle discovered this relationship between volume and pressure. I'm going to use his name. I am not going to test you on the names, okay? That's chemical history, and we're not studying history here. So we do call it Boyle's Law. I personally have a hard time remembering what the names of them. The important thing is that you learn how to do the problems. So here we have constant temperature and constant amount of gas. Because if you allow the temperature to change, that's going to mess everything up. So what Boyle's law says is that the volume is inversely proportional to the pressure. The volume is proportional to 1 over the pressure. So if the volume increases, the pressure must decrease, and vice versa. That's all very nice, but the more useful expression is this one. P1V1 equals P2V2. So the pressure times the volume in one circumstance is equal to the pressure times the volume in a different circumstance. These experiments were done, see, when did he live? Back in the 1600s, okay? They didn't have electricity or anything then. Didn't know what atoms were. So very simple experiments, simple equipment. So a J-shaped tube, closed on one end, open on the other end, with some mercury in it. So there's some gas trapped in here, some air. And the mercury is higher on this side than on that side, because this gas has been squished together and it has a pressure, and its pressure is greater than the atmospheric pressure. If this was open on this side, then just like with water in a tube, it would be the same level on both sides, right? Because it's lower on this side, that means this pressure is larger than the pressure over here. You can measure the difference in pressure with a ruler, measuring the difference between the levels of mercury. What he found was if you add a bunch of mercury here, that's going to squish this gas even more. And now we see that the difference is larger. The gas volume is smaller, and the pressure difference is larger. So you take this data and you graph it. So the volume of the gas here against the pressure. When the volume is large, the pressure is low, and as the pressure is increased, the volume gets smaller and smaller. So here's some graphs I made. This graph shows a curve, right? And curves are a little hard to quantify, and so we like to figure out how can we get a straight line from our data. Well, instead of graphing volume versus pressure, we're going to graph volume versus 1 over pressure, the inverse of pressure. And when we do that, then we get a beautiful straight line. So the volume is proportional to 1 over the pressure. Kinetic molecular theory helps us to understand this. Here we have a container with a gas in it. This volume is 1 liter. You can count the number of particles. It's the same here and here. And you've got a weight on the lid here, and the pressure is 1 atmosphere. If we put a larger weight here and push the lid down so this volume has half the size, then the pressure goes up by a factor of 2. So they're changing by the same factor. One went down by a factor of 2, one went up by a factor of 2. Why? Well, when these particles are squeezed into a smaller space, they're going to run into the sides of the container more frequently, and so the pressure is higher. Any questions? So we can calculate volumes or pressures using Boyle's law, and we talk a lot about cylinders and pistons. So there's a definite strategy to how to approach these problems. You definitely want to read through the whole problem, but then we're going to focus on the numbers, okay? So a cylinder equipped with a movable piston has an applied pressure of 3 atmospheres, a volume of 5 liters. What is the volume of the cylinder if the pressure is decreased to 2 atmospheres? Okay, so let's pull the numbers out. A lot of gas problems are going to have us dealing with changing circumstances here. So this one had a movable piston, and here we have a word indicating change. Something was decreased, right? So we have 2 circumstances, the first one and the second one. So I find it useful to make a table. And so we're going to have situation 1 and situation 2. The order of them doesn't matter. We're going to go through this problem and just write down the information. So the first number we come to, pressure of 3 atmospheres. So I'm going to write that here, 3.0 atmospheres. And atmosphere is a unit of pressure, and they told me that that was the pressure. So I'm going to call that column pressure. Pressure of 3 atmospheres and volume of 5 liters. Those two go together. This and that. The 2 things go together. So I'm going to call both of those situation 1. So 3 atmospheres and 5 liters. Now that looks like an 8. 5 liters. Liters is a unit of volume. This is the volume column. You with me so far? We keep reading. Blah, 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 blah. 2 atmospheres. Well, 2 atmospheres is a pressure, so I'm going to write that in the pressure column. 2.0 atmospheres. Now I have a table, and I have 1 blank. I should have 1 empty square. Let's look at the question word, what? What is the volume? This is a volume. This is the volume when the pressure is 2 atmospheres. So this is my question right here. Because this is volume in row 2, I'm going to call that V2. Very original, right? I have now labeled all my stuff. This is P1, this is V1, this is P2, this is V2. So I'm going to use Boyle's law. P1 times V1 equals P2 times V2. I have 3 of those numbers. I can solve for the 4th. It's best to rearrange the equation before you stick numbers in it. Okay? So I'm trying to get V2 by itself. Now, some of you might have some difficulties rearranging equations. If you do, please come and talk to me, and I can help you, okay? You have to learn how to rearrange some simple equations here. So we want V2 by itself. We need P2 to go away. We need it to go to the other side of the equal sign. So what I'm going to do is I'm going to divide this side by P2. Because P2 divided by P2 is 1, and 1 doesn't matter. So I can make it go away. But in order for this to remain an equality, I have to do the same thing to both sides. So I have to also divide the other side by P2. And that's how I rearrange the equation. It's kind of messy there, so I'm going to rewrite it. V2 is equal to P1 times V1 divided by P2. It is super easy to get the 1s and the 2s mixed around. So go back over it and make sure that you copied it down correctly. Now all I have to do is look at my table and pull out the values. So I need P1, so there's P1, 3 atmospheres. Always, 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 always write the units in your equations. Times the volume 1, 5 liters, divided by P2, and over here, there's P2. Check out the units. See what cancels. Well, the atmospheres cancel. I'm left with a unit of liter. That's good because I'm solving for volume. So I've got 3 times 5 divided by 2. So volume 2 is 7.5. That's what my calculator shows me, liters. Is that the right number of sig figs? Yeah. All of my numbers here had 2 sig figs, and so I should end up with 2, and I did. Any questions? When you're scuba diving, understanding how gases work is really important. For every 10 meters that you go under the surface of the water, you experience an extra 1 atmosphere of pressure. And so in order to be able to breathe, the air tank has a pressure regulator on it. It has to regulate the pressure and give you a higher pressure of air, otherwise you're not going to be able to expand your lungs. So here he's 20 meters below the surface. Every 10 meters is 1 atmosphere of pressure. So 1 plus 2 is 3. So he's got 3 atmospheres of pressure here. That means that the pressure in his lungs is also 3 atmospheres. If you ascend too quickly, and especially if you're not exhaling as you ascend, you get to the surface where you still have 3 atmospheres of pressure in your lungs and only 1 atmosphere outside. You can cause some damage to your lungs. Not a good idea. I don't like this problem. We're going to do it anyway. A snorkeler takes a syringe filled with 16 milliliters of air from the surface, where the pressure is 1 atmosphere, to an unknown depth. The volume of the air in the syringe at this depth is 7.5 milliliters. What is the pressure at this depth? If pressure increases by an additional 1 atmosphere for every 10 meters of depth, how deep is the snorkeler? Okay, so this problem is a lot more complicated. It's got a lot more words than the last one. We can still do this, though. We're going to take the same approach. We're going to make a table. We're going to fill it out by putting in numbers. So the first number we come to is 16 milliliters. Milliliter is a unit of what? Volume. So I'm going to call this column volume. Where the pressure is 1 atmosphere, so 1.0 atmospheres, and that's a pressure, so I'm going to call that column pressure. And then the next number we get to is 7.5 milliliters. Well, that's a volume, so I want to put that in the volume column. I have one blank. I look at the question word, what is the pressure? Oh, well, that worked out pretty well. P2, that's what I'm solving for. So Boyle's law, well, let's do it the same way every time. P1 V1 equals P2 V2. I need to rearrange this equation to get P2 all by itself, because that's the variable here that I need to find. So I'm going to divide by V2, so the V2's cancel out, and I have to divide the other side by V2. So P2 is equal to P1 V1 over V2. Then I take the numbers from my table and plug them in, being careful to get them in the right place. So pressure 1 was 1 atmosphere. Volume 1 was 16 milliliters. Divide by volume 2, 7.5 milliliters. Cancel units. Milliliter divided by milliliter goes away. So I have 1 times 16 divided by 7.5. And my calculator is giving me a whole bunch of numbers. How many sig figs should my answer have? 2. So 2.1, and then it's 3.3, and it just keeps going. Atmospheres. So the answer to the first question, what is the pressure at this depth? 2.1 atmospheres. Any questions about that one? So that's the answer to one question, but there's another question. If there's 2 questions, we better come up with 2 answers. This is the part that I think is a little bit tough for 3A. So how deep is the snorkel? If the pressure increases by an additional 1 atmosphere for every 10 meters of depth. So that is telling us that one atmosphere is equal to 10 meters of depth. Well, at the surface, we had a pressure of 1 atmosphere, right? So how much has the pressure increased? 1.1 atmospheres, right? So we have an increase of 1.1 atmosphere. I can use this as a conversion factor to convert that into meters. For every 10 meters, you get an additional 1 atmosphere. So that tells me that it's about 11 meters. The A student should be able to do that. Everybody else, if you get this, you're good. Any questions?